So we move to the last talk of the conference. So Miguel is going to tell us about the Nielsen realization problem. Miguel?
Thank you very much, Rodrigo. Thank you very much for the invitation. It's a pleasure to be in Miami. I want to tell you about some joint work with my PhD student, Colin. That is mostly taken out of his PhD thesis, still in progress. So I'm going to talk about the mapping class group. So in the classical setting, the mapping class group of an orientable surface of genus G is just the group of path components of the orientation preserving diffeomorphisms of the surface. And that can be thought of also as the group of diffeomorphisms, the orientation preserving diffeomorphisms, modulo the diffeomorphisms isotopic to the identity. So this group is very important in topology, low dimensional topology, has relations to Teichmüller theory and whatnot. And also, it is related to stable homotopy theory in this way. So it turns out that when we stabilize the genus, G is large enough, the rational cohomology of the group becomes polynomial algebra on the so-called Miller-Morita-Mumford classes, kappa i's. Related to the group as well is this the so-called Nielsen realization problem that was posed by Nielsen roughly in the 30s, in the 1930s. This is a question that asks whether a finite subgroup of the mapping class group can be lifted isomorphically to the diffeomorphism group, right? And Nielsen and other authors did some specific cases, and the problem was finally solved by Kerckhoff in the 80s, right? Now one can state Kirchhoffs Theorem in a certain other way. So we know that the mapping class group acts in Euler space of complex structures on the surface modulo those isotopic to modulo diffeomorphisms isotopic to the identity. One way to state Kirchhoffs theorem is to say that every finite subgroup of the mapping class group acting on the Teichmüller space has a fixed point, right? One can improve this result by adding some decorations, say mark points on the surface, and it's essentially a theorem of Wolper from the late 80s that every finite subgroup of the extended mapping class group, here we consider orientation preserving and orientation reversing diffeomorphisms, acting on the corresponding Teichmüller space for a surface with k mark points, has a fixed point, all right? So yeah, it's essentially a result of Wolper. So now people has recently started looking at non-orientable surfaces, and the way you define the mapping class group, in this case, is just by looking at all diffeomorphisms of the surface and dividing by the connected component of the identity. And although it might be well known among the experts, we couldn't find a written proof of this fact. So I asked Nestor to prove this. And what he showed is that every finite subgroup of the non-orientable mapping class group acting on the corresponding Teichmüller space has a fixed point, right? And the way we do this is by thinking of Klein surfaces, right? So we you have to switch from three main ingredients related to Riemann surfaces to the world of Klein surfaces, to the non-orientable world. Right?
Like if you have a diffeomorphism of NG, can you lift it to like the NG has like some Zeeman 2 cover?
That's right. That's right. Yes.
It lifts, no? Right?
Yes.
But then and you lift the G to a double cover of G, right?
Right. Right.
Then that would have a fixed point on the diagonal space.
Yes. Actually, double, twice as many.
Okay.
Yes.
Cool.
Yes. No, that's exactly right. That's exactly right. So, so you have to compare diffeomorphisms of the non-orientable surface and the orientable double cover, the corresponding mapping class groups, and the Teichmüller space.
Yeah, okay.
So that's what we have to control. And so, so we want to think of Klein surfaces, which are the analogs of Riemann surfaces, where you allow change of coordinates to be analytic and anti-analytic. So a function is said to be de-analytic if it is either analytic or anti-analytic in connected components, right? And so by requiring the change of coordinates to be de-analytic, you get the concept of a Klein surface structure. So you can think of a dianalytic atlas in this way. You can also think of the set of dianalytic structures on a surface sigma, right? So this concept contains all Riemann surfaces, but allows non-orientable surfaces as well. Right. So so a morphism of Klein surfaces is just a map that is compatible with the analytic charts, and given diffeomorphism and a Klein surface structure, sigma, you define the pullback of the original structure by the only structure to be the only structure, so that this is a morphism, right? So now you think of the orientable double cover, right? So an orientable double cover of a Klein surface is a Riemann surface equipped with a involution, so that the quotient is by is the given surfaces, the given surface, and so that the quotient is so analytic unramified double cover.
Does that mean with the surface? Is that? I guess. Oh yeah. So that means probably is S has to be equal to S bar.
This is what happens. So you start with a Klein surface in G.
Yeah.
Right. And you look at the. You can construct a double cover with all these structures. You can. So NG is a Klein surface equipped with a given structure. So you can construct a Riemann surface together with an anti-involution.
So what I'm asking is,
yeah.
Does every Riemann surface emit like an anti-involution like that? I'm guessing not. Like maybe even what is the dimension of the moduli space like NG?
No, I don't think. I think it depends on the structure. Yeah. 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 Yeah.
But can you regard NG as kind of the ring of the stack?
Sorry?
I think every point has to. Can you regard NG as analytic stack? Every point has to. I mean, this formalism of giving this analytic structure of NG can be equivalent to
Well, you're just lifting the structure, I guess. I don't know. Yeah. So the thing is, you want just for the projection and sigma to be dianalytic, and that's it.
Yeah. Okay. I mean, I think I get. I mean,
So you want this covering map to be compatible with all the structures.
Yeah.
So so given Klein surface of I don't know either finite genus, you can always construct a Riemann surface equipped with this involution and a Riemann surface structure, so that everything is dianalytic. All right. So yeah, that's what you were wondering. So every diffeomorphism of the Klein surface with k fixed point, k mark point, admits exactly two liftings to the orientable double cover, and exactly one of these preserves orientation. So this choice induces a commutative diagram of this sort. And so to go from diffeomorphisms with k mark points to diffeomorphism of the orientable double cover with twice as many mark points, and that map passes to the mapping class groups. And what it was observed by Hoppe and Tillman is that the map at the level of mapping class group is always injective for j bigger or equal to 3. In the case you don't have any mark points, and that is always injective for every genus, provided you have at least one mark point, and that was observed by Da Silva Gonçalves, John Waskey, and Miguel Maldonado not long ago. All right. So now, if you have a Klein surface, you can construct the analog of the Teichmüller space. So this you can start with a Riemann surface in the orientable case, with a non-orientable Klein surface, and so what you do is divide, take the set of all the space of all structures and quotient them out by the isotopy relation. So you get the Teichmüller space of the surface with k mark points, which turns out to be a Euclidean space of dimension 6g minus 6 2k in the orientable case, and roughly in the non-orientable case. Well, moreover, you have the double cover of the Klein surface of genus G. Then you have a corresponding map between the Teichmüller spaces, which is also injective, right? Which sends the class of the structure X to the class of the pullback of X under the covering map, and you can identify what the image of Paris star is, right? So it's basically all those structures that are invariant under the map induced by the involution. All right. So so this is how you show. Yes.
But the ones, so the sigma is like a fixed involution now for that, like where sigma is, because before sigma was like an involution on one surface.
Right. So
here sigma is like kind of fixed to all surfaces.
No, you fix your Klein surface in G look at the orientable double cover
Of
that
that.
comes equipped with a sigma, so that
Okay.
the quotient is the original
Yeah, I got
client
it. That-
surface.
That induces an automorphism on the Teichmüller space.
Yes.
In fact, an involution on the Teichmüller space.
Right,
Yeah.
and
Okay.
that allows you to identify the image of this map.
Yeah, and I think in the algebraic geometry language, it's just sending a curve to the complex conjugate of the curve.
I think it's, yeah. So then we have these maps. We have the injection from the mapping class group of the non-orientable surface, okay, with KMR points to the mapping class group of the orientable double cover with twice as many mark points, and the injection between the corresponding Teichmüller spaces. Moreover, we know the mapping class group acts on the Teichmüller space by pullbacks, and all this information groups together equivalently in this way. So for any element of the Teichmüller space, the non-orientable surface, and an element of the mapping class group of NG, then we know that pi star is equivalent with respect to phi, right? So now you can show that every finite subgroup of the mapping class group of the non-orientable surface with KMR points acting on the corresponding Teichmüller space has a fixed point. And this is the way you do it. So you start with a finite group here, and you lift it, right, to the mapping class group of the surface upstairs, right? And then you think of the group generated by the image of and the class of the involution sigma, right? It turns out this group is just the product of G times C2 that lives in the extended mapping class group of the orientable surface, right? So Boltberg's result tells you that this new group has a fixed point, right? And in particular, it's fixed on the action of sigma, right? That tells you that this Y, the structure Y, is invariant under the action of sigma, and thus it is in the image of pi star, right? So we have, so the class of Y comes from a class in the Teichmüller space of the non-orientable surface, right? And then one showed that this point is precisely a fixed point for that, for the original group. So that's how you do that. So now, so that's the story for finite groups. So what about infinite groups? So let me just say very quickly that so if you think of the orientable case, let's see, it's well known that this projection doesn't have a section for G greater or equal than 5, right? And so in the case of the torus, I guess, the mapping class group is the group SL to Z, and this is well known to have a section. And it's a result of Morita that there is no such a section for G greater or equal than 5. In the non-orientable case, you say take G equal to 2. So you're thinking of the Klein bottle. But in this case, this group is C2 cross C2. So it's finite. So you definitely have a section. And in the case of genus 3, this is GL2Z. And it was also proven by González Acuña and Marquez Bobadilla that this projection has a section using the fact that N3 is the blow up of a torus at one point. All right, so what we're able to show, I mean, extending the methods of Morita, for large G, the projection for the corresponding non-orientable groups does not have a section, right? And this is how you do it. You use characteristic classes, right? You can start, well, this is the story for the orientable setting. So you have if you have a smooth orientable surface bundle, then you can always take the vertical bundle, right? That's a vector bundle of dimension 2. So you can raise the Euler class to the n+1 and apply the Umkehr map associated to this this bundle of the Gisin map, right? And get a class in dimension 2n of the base. So yeah, non-orientable setting, I mean, we cannot do this construction. We need orientation to use the Euler class. So what you can do is turn to stable information. Namely, you can pass. Yeah. Look at the so-called between the suspension spectra V to the suspension spectra V. So was and look at the induced mapping cohomology, right? So one of the properties that this has is that when you compose the map induced from the projection with transfer, you get multiplication by the Euler characteristic of the fiber, right? And also, so what you know is that the transfer is given by the Schritt map applied to the class multiplied by the Euler class.
That in that the diagram is the middle F supposed to be V, or is it just
The what? The middle?
F in the diagram with the chi F below it, like the curvy arrow like right above?
Right, that multiplication by the Euler characteristic of
No, but is it supposed to be an H star E in there, or just really is supposed to be an H star? It's like C upper star goes to H star.
Right, I think it's yes, E. Sorry about that. Yeah, my bad. All right, so well, this is another definition of the kappa classes. And you can think of a kappa n to be the image on the transfer of the Euler class, this bundle raised to the upper n. And so in even dimensions, you know, the kappa 2n is the map induced by the transfer applied to the n power of the first Pontryagin class, right? So this is what we use to define the analogous classes in the non-orientable setting, right? So in the non-oriented case, you start with a bundle of non-orientable surfaces, right? Think of the Becker-Gottlieb transfer, right? And take the I power of the first Pontryagin class, or the vertical bundle, right? And get a class in dimension 4i on the base, right? And well, this class are compatible with the Mumford Morita Miller classes. So if you have a surface bundle, fibers are non-orientable, and you think of the orientable double cover, then there's a natural way which you can compare them, right? So now, if you apply this construction to these the universal surface bundles with fiber Ng or fiber Sg minus 1, then you get back the kappa classes, right? And these new classes that live in the cohomology of the mapping class group of the non-orientable surface. So I mentioned the theorem of Miller, Morita, and Haar before. What you get in the non-orientable case is that the cohomology of the stable mapping class group, the non-orientable mapping class group, is given by a polynomial algebra on these classes zeta I, right? So there's a map from the polynomial algebra on zeta i's to the cohomology of the mapping class group that is an isomorphism in this stable range. Since the zeta i's live in dimension 4i, then this means that they're not going to be zero in cohomology if the genus is at least 16i plus 3. So also, what happens with the non-orientable and the orientable mapping class group, and it turns out that the image kappa 2i is twice you give the group of diffeomorphisms the discrete topology. You can prove that there is no section. If you had a section, then this composite will be the identity, right? In particular, the image of zeta I will be non-zero if E is greater or equal than 16i plus 3. But for instance, if I is equal to 2, then zeta 2 is non-zero if the genus is at least 35, right? So you get a contradiction this way. All right, that's it for the non-existent of the section. And let me talk about cohomology of these groups. So all these mapping class groups have finite virtual cohomological dimension, which means that they contain a torsion-free subgroup of finite index. And for those groups, we can define the so-called Farrell cohomology using a complete resolution. So Farrell cohomology is an extension of the Tate cohomology for finite groups. And here I have a few basic properties. local dimension. These groups are torsion groups, so you can decompose them as the product of the p-periodic components. So they might be periodic. So one says that the p-periodic component of this group is periodic if there is a D, so that you have isomorphisms of this sort for every I. And you also have Brown's formula that tells you that the p-periodic component of the Farrell cohomology of the group gamma is the product of the cohomologies of the normalizers. Or this product runs over a set of conjugacy classes of the subgroups of order P in the group. Right? So one has to get a decent computation. You have to show that the groups we're looking at are periodic, are p-periodic, say, and identify the normalizers. Right? So you have a group of that sort. So gamma eventually is going to be one of these mapping class groups. But let's suppose for the moment that gamma is a group of finite virtual cohomological dimension that contains of prime order P, right? Let's say that P is not prime by the moment. So so we know that gamma contains a torsion-free subgroup of finite index, right? So then an order of a group of finite order P maps isomorphically to the quotient, right? And we know what the cohomology of this group looks like is just exterior on a class of dimension 1 times polynomial on a class of dimension 2. So you can restrict the cohomology of gamma to the cohomology of pi and look at the reduction modulo P inside the mod P cohomology of pi, right? So you know that this image is going to lie in a polynomial algebra of this sort, generated by the class U2, certain power m, right? Maximum m, so that happens, right? And for these pair of groups, one defines the Jagged invariant as the least common multiple of twice this m, right? For pi running inside of gamma of order P. And what one can prove is that if gamma is a p-periodic group of finite virtual cohomological dimension, then the p-period of the group gamma coincides with the Jagged invariant. That's what happens. So using this tool, we're able to show that we can extend it for mark point. If this mapping class group contains p torsion, then the p period is 4. It's 4. So somehow in contrast to what happens in the orientable case, where the p period is usually 2. All right, so this is what we do. We have a subgroup of order P inside the mapping class group of the surface NGE with 1 mark point. So we can lift it to the diffeomorphism by the Nielsen realization, right? And then we can represent the diffeomorphisms by taking a diffeo F to with one fixed point to the differential from the tangent space of the surface at that fixed point to itself, right? So when you restrict that to to the group for the P, then you get a faithful representation inside JL2 plus of R. So now, being that a faithful representation of C mod P, you get a first chance class, which is non-zero, right? And to know that when you pass to classifying spaces, the cohomology of the classifying space of GLR has Pontryagin class, dimension 4, that hits twice the not twice the square of the chunk class of BGL 2 plus, right? And so so it's going to hit something non-zero here, right? And so that's going to give us something non-zero here, right? And that means we're going to, so there's going to be some information contained in dimension 4, and since we were taking twice this, then M, this M is going to be 2 times 2 is 4, and that's how we get that the period is show that the period is exactly 4. But this is how the idea behind that. All right. So how about the normalizers? So one has to count the conjugacy classes of subgroups for the P inside the mapping class group, and look at the normalizers. And we do that by looking at the fixed point data. So this is how you define the fixed point data for a diffeomorphism, or for the P. You can do it more generally, but say that if you have a small P acting on a surface, then you look at the set of fixed points. So in every fixed point, the diffeomorphism acts by rotation with respect to some fixed Riemann surface structure, right? And well, you can raise this generator to a certain power beta I, so that this power acts exactly by rotation by 2 pi I over P, right? So these powers beta I give you an unordered tuple. It's an unordered T tuple, and these are known as the fixed point data of a diffeomorphism phi. So it's well known that if you have 2 diffeomorphisms for the P that are conjugated, then the fixed point data are the same and vice versa, right? And moreover, one knows that the fixed point data depends only on the isotopic class of phi. So this definition passes to the elements of the mapping class group. And in the mapping class group, one also knows that 2 elements are conjugated if and only if the corresponding fixed point data agree. So so we can do that for orientable surfaces for map points, and we can pass to the non-orientable case. So in this case, you take a diffeomorphism for the P of a non-orientable surface, and you can define the fixed point data in the same fashion. But the thing is, these betas are well defined up to a sign, right? So we're forced to introduce some equivalent relation or some congruence of some sort.
something about the diffeomorphism more than just being diffeomorphism? Like to make sure it has like isolated fixed points. Like I think if it's oriented to preserving or not. Is it obvious that it has isolated fixed points? That diffeomorphism would have like, you know, not like a whole line of fixed points or something, a whole line of circle. Or maybe you're just assuming that it does. That
Yeah.
you have an isolated. Yeah. Okay.
I think you can always show that for even structure, yes, of the surface.
Yeah, because I was saying maybe for oriented surface, maybe they give plus force to have an isolated point. I don't know. Like what I'm imagining is like if I have a torus or like a genus 1 torus, and I like, you know, I could like reflect it like along some line of maybe 2 circles that would be fixed. That wouldn't be orientable. I mean, that wouldn't be orientation preserving.
Right. No. So
Even if you had like a 2-hole donut, you could reflect it across one way. Do the same thing. But it still wouldn't be orientation preserving.
no, but now we're in non-orientable case.
Yeah, so then that's what I'm asking. If you need to, yeah, actually, what I'm asking, if you're in diff ng, you want to know that it lifts to the orientable double cover as an orientation preserving map. Is it like, I'm wondering if you could have diffeomorphism of ng, which still don't, when they lift them, they're not orientation preserving.
Well, you always have to lift things, and one of them is orientation.
Oh, one of them. Oh, yeah.
Right,
You said one of them is orientation preserving.
Yes.
Oh, I see. Yeah. Oh. Yeah.
So long story short, I mean, you can do all these with for a diffeomorphism of order P of ng with KMR points, right? And the way you define the so you define the fixed point data in the same fashion, but now the first K betas give you an order tuple, and they're associated to the K. Well, they're the fixed points of the associated KMR points, and the rest of them is thought of as a T minus K unordered tuple, right? So we have a similar notion of congruence like before, and this notion is well defined when you pass to mapping class groups. And well, what about the p-periodicity? Well, first you have to ensure that that the group contains p-torsion, right? To make all these run, and well, if you have a subgroup of all the p acting on the surface, you can look at the quotient as of the surface by this group C mod p, and think of it as a ramified cover, right? So it better satisfy the Riemann-Horowitz equation, right? And moreover, if the genus is of this tree, and you're thinking of an odd prime, then if the mapping class group has p-torsion, then it has p-periodic cohomology. So one can show that. So
always on. Is P always on?
Yes.
Okay.
Well, I mean, for us, it's odd. So,
Yeah, that, I think that answers my question.
Yes. We're just considering P odd in this case. Yeah. And I mean, whenever you have those conditions, then what you can show is that the conjugacy classes of order P subgroups in the mapping class group with non-orientable mapping class group with KMR points acting on the surface with Diff fixed points are in one-to-one correspondence with these tuples, congruence classes of T-tuples of given by the fixed point data. Right? We can normalize them so that the first one is 1. So you can identify the list of conjugacy classes in several cases, and one very easy case is the case when the genus is equal to P, and in that case, and say that the number of mark points is 1 or 2, then the normalizer of this CMOS P can be shown to be the dihedral group of order 2P, whose cohomology is very well known, and thus by Brown's formula, the Farrell cohomology of the mapping class group of a genus P surface with K mark point is given by this formula, at least for K equal to 1 or 2. That's probably what I wanted to say.
All right. Let's thank Miguel. Question.
Go back to the previous slide. Just the one previous. No, what I was gonna ask, but I think it might have been answered on the slide. Like, you know, whether I think in the orientable case, like kind of Riemann-Hurwitz or something. Hurwitz formula says that there can be an automorphism of a curve, any finite group of automorphism of a curve of G has to have less than or equal to 84 G minus 1.
Yes.
Is there a similar thing? So that's saying something, that's talking about fixed points of a finite group acting on a point in
For a given
space.
structure, yes.
Yeah.
Yes.
Is there an analog of that in the unorientable
I
case?
think there's something like that, yeah. I don't know.
Oh, the exact,
Precise
because
number,
what
yeah.
would probably be 8 less than 84 G. I know it's.
On the other hand, if you have any finite group, you can always realize it as an automorphism for a large enough genus, I guess.
Oh, any finite group.
I think so. So there might be something going on with symmetricals acting on large genus surfaces.
Yeah, okay, I'll go ahead.
Other questions? Well, if not, let's thank Miguel again. Thank you very much for coming.